So hello, I'm Alec Wolman. I'm currently a research manager in the office of the CTO team in Microsoft's Azure for Operators organization. And before joining Azure a year ago, I worked in Microsoft research for 19 years, working on a variety of topics in computer systems, networking, and security. So today, I'd like to introduce our two panelists. Dr. Lihua Yuan is currently a partner software engineering manager in Microsoft Azure Networking. He leads the network platform team supporting the network infrastructure, connecting major businesses in Azure, Microsoft 365, and Bing. His team drove the network hardware evolution from the 10 gig generation all the way to the 400 gig generation in Microsoft. His team led the development of the open source Sonic network operating system that is widely adopted in industry. And they also developed software automation that manages the whole life cycle of the network. Lihua's work has led to multiple research publications at top networking conferences, and he is an incubation committee member at the Open Compute Project since 2018. Next, I'd like to introduce Daniel Firestone. Daniel is the engineering director for the Azure Host Networking and Hardware Acceleration team. Daniel's team builds Azure's Host SDN stack, SmartNICs, RDMA transports, and network and storage acceleration platforms. Daniel has been working on Host SDN in Azure for 10 years. Previously, he did his undergraduate studies at MIT. Okay, so the topic for today's discussion is high-speed networking and the role that specialized hardware plays as network link speeds continue to grow. One of the fascinating trends over the last decade is that network link speeds have continued to grow at a significant rate, and they've outpaced the growth of CPU speeds by quite a bit during that same time period. Okay, so to start off, I'd like to talk to both of the panelists and say, can you both tell me a little bit about your history at Microsoft beyond what I've introduced in the bio? I'd like to hear a bit about the projects that you've led and what were the key problems you were trying to solve and what was the impact?
Sure. Thank you, Alec. So I joined Azure about 10 years ago. And the first thing we saw in the host networking space was really two major trends that were converging. One was the growth of what would become high-speed networks. 10 gig NICs had been around for a long time, but hadn't been widely adopted because they were expensive. The network was expensive. But as merchant silicon-based networks were being built, suddenly we saw a huge increase in the potential speeds of the networks, both to 10 gig, and we saw that 25, 40, 50, 100 was likely to be not far behind. But at the same time, we also had this emerging trend of host-based software-defined networking, or SDN, where the clouds were essentially building virtual networking stacks. This was originally based on research that Microsoft Research did on VL2 and similar projects. And people were building virtual network stacks to allow customers onboarding to the cloud to create their own virtual networks as if they were running their own data centers. So if you set up your own physical topology on premises, you could build your own logical topology. And so we were using the CPUs to do all of that network packet processing to make that virtualization work. And there were a bunch of teams excited about adding all kinds of new SDN features in the CPUs, and a bunch of teams excited about scaling up network speeds and building very fast physical networks with all this merchant silicon. But these two trends were, in some sense, very much at odds when they met at the host. Because the network speeds, as you said, Alec, were growing faster and have grown faster over the last decade than the CPUs. And so the challenges I took on were really around sort of merging those two trends. And at first, that was about just building faster vSwitches and building much smarter logic in the vSwitches to do smart caching and smart compilation of SDN policies and sort of try to keep up with the 1 gig to 10 gig transition. But as 10 to 40 started to happen, it was very clear that we had to do some form of hardware acceleration. And I eventually started what became the Azure SmartNIC program, where we used FPGAs to build our own SmartNICs that could offload a lot of this policy, but still keep them programmable. And so we chose these programmable FPGA-based devices as the way to do that. And since then, we've taken on sort of transport problems with RDMA, a set of network virtualization technology and hardware where we started building storage virtualization and accelerating storage and hardware. And that trend has only accelerated from there. And it's continuing to be the case that the network is growing faster than the CPUs. So I don't see those trends going away. But those are the key problems I've worked on solving in my career here.
Thank you. That's great. So let's hear from Lihua, and then I'll ask some follow-up questions.
Cool. Yeah, thanks. I joined Microsoft in 2008. So at the beginning, I started working on a problem that what do we call it? Software load balancer. Right? That's widely used today as a part of the overlay network. Right? That's actually a very long collaboration with MSR at that point. Right. So after that, I moved on to work on the network management stack, as well as enabling the VR2-like cloud network in the bin, right? And basically using BGP as a kind of data center IGP work, right? With the industry together. So also developed quite a bit of different monitoring diagnostic capabilities in the system. After that, we started working on the Sonic operating system. So for the last few years, kind of marching on the agenda of making Sonic the default OS across the board in Azure. We also picked up some hardware projects recently in the dual top program, that what we call Gemini, the smart cable kind of work, right? To basically catching on the industry trend of smarter devices across the board, and then even lowering the cable, right? To make programmability there to enable new scenarios.
Thank you. That's awesome. Let me start with a follow-up question for Daniel. So you talked about your work in sort of building FPGA hardware acceleration for NICs. So in the abstract, we know that it's fairly easy to characterize the engineering trade-offs between sort of building functionality in software versus building it in FPGAs versus building custom ASICs. But now that you've had actually a number of years deploying accelerated hardware for hosts at really a tremendous scale, I really like to hear how your experiences changed your views on these trade-offs.
Sure, that's a great question, Alec. And I think the most interesting thing that's happened in this space has been sort of how some of those categories have converged and merged in their own interesting ways. And when we started off, I would say the categories that you could choose to do sort of host-based packet processing were exactly the ones you mentioned. You could take kind of a custom ASIC, which would be a NIC that one of the commercial NIC vendors would sell. You could do all your packet processing in software and essentially go burn x86 cores. Or you could take the path that we initially took, which was to use FPGA-based technology to build sort of hardware circuits, but in a programmable and updatable fashion to try to merge the benefits of a programmable CPU stack with hardware. And there was also probably a fourth category of people sort of building NPUs and sort of classic network processors. I think the big thing that happened since then is these techs starting to merge. The first big industry sign of this, I think, was what Amazon did with Nitro, which is now a pretty well-known brand in this space, where they said we're going to tape out an ASIC, but we also want the data path to be programmable, so we're going to make the data path out of ARM cores. And you start to look at this thing. Well, is this an ASIC or is it actually a CPU? If you look at where the power and cost of this thing is going, it's actually a bunch of CPU cores. Now, of course, there's some ASIC logic to run things like your Macs and accelerators and encryption blocks, but you start to find that you have a significant amount of your silicon going into programmable elements. When you look at the FPGAs, they also started from a space of, well, everything is a reconfigurable circuit. But as they moved on, you started to see a whole bunch of ASIC logic for all the sort of same things that the CPU-based programs built, things like Macs, encryption, et cetera. And the programmable elements instead of CPU cores would be FPGA gates. And then if you looked at the traditional ASIC NICs, they wanted to get into the smart NIC game as well. And so they would put some CPU cores next to their traditional NICs to do some programmable management processing. And they started to take sort of the classic fixed function pipelines in those NICs and make them a little bit more programmable, put some lookup tables into them. Now you've got a set of emerging players that sort of are taking a lot of the same sorts of technology as Nitro and building programmable elements in CPUs or taking ideas from NPUs. And and it's no longer super clear in this space whether you can categorize as anything an ASIC, an FPGA, or or a CPU. Which have you picked? Almost all of these strategies now merge some amount of ASIC logic with some amount of programmable logic, and so I think the question now has become, what's the right unit of programmable logic? How do they scale? And some of what we found is the FPGA logic does really well for sort of packets per second per unit silicon area. Like if you want to do a programmable function at very high performance, they'll usually do a little better than the CPU cores. But the CPU-based approaches will do better if you want sort of arbitrary burstability, because rather than sort of laying out a circuit design, you can scale up and down software across the cores. So I think those trade-offs have been interesting to watch. Quite frankly, in the industry, what's winning right now is whoever manages to get the latest speeds and feeds grades out faster. So in some sense, we can talk about is one of these, 10 watts, 20 watts more expensive than the other, but it's usually sort of who gets the fastest speed out first. So I think, you're going to continue to see interesting mixes of these designs, but ultimately execution is what wins here.
That's very interesting. Yeah. So that really sort of puts a little bit of a ding on sort of the time cycles of ASIC approaches then, because if speed and agility is really the thing that's most important, then yeah, that's very interesting.
I think we're still seeing ASIC cycles when you want to go upgrade your speeds. People are going from 50 gig to 100 gig to 200 to 400. Those are racing ahead of the CPUs. I mean, anytime you want to go put a faster pipe on it, you're going to tape out a new chip. But yeah, I think within those cycles, you're seeing that programmability.
Awesome. Okay. So Leewa. So with Sonic, the open source network switch operating system, I know that one of the significant goals that you had was to reduce operational complexity by being able to run sort of the same software stack across different Swiss ASICs from different vendors. I'm wondering kind of how well has this worked out, and were there any significant surprises that you experienced along the way?
Yeah, I think I would definitely say that it worked out for us very well, right? So we were able to onboard quite a few more ASICs, which would probably be impossible in the past. Right, so we basically took the software abstraction one layer down, right? Instead of purely running the management stack down to the OS level and absorb the hardware differences at the switch abstraction interface level, right, SI level. Right, so that allows us to kind of work with multiple ASIC vendor, leveraging the newest and shiniest ASIC, or even just in the same generation, but multiple, to kind of strengthen our competitive position and ecosystem, right? So and also that the other angle of it, right, is also that we are with this open source effort, right, we're kind of really started to be able to accumulate learnings from our daily operations, right, and keep on just improving the OS quality very quickly through the internal and community-wide collaboration, right? So I think that's definitely a very good experience for us. Yeah. In terms of a surprise, I would say that maybe the biggest surprise throughout the journey of Sonic, right, is that the really a pleasant surprise for the amount of things we can learn from the community. Right, at the beginning of Sonic, right, we are targeting basically the pizza boxes, right, the single ASIC devices, which are relatively simple. We felt that the big chassis, those are giant one rack, full rack kind of a switch devices, right? It's really complex hardware, and felt like that's going to be very, very complicated. Right? But I think through the community collaboration, a lot of engineering being poured in to kind of simplify it, redo the abstraction, right? So coming together towards all this, eventually land on this disaggregated chassis kind of model. That basically is a cross network in the chassis, right? In a different form, right? So once we kind of get that light bulb moment, right, the community kind of was able to kind of just gear together and working towards a kind of Sonic chassis kind of model, and still being able to reuse it, the software across a different chassis with different hardware chipsets, right? So I think that's a very pleasant surprise that how much we can learn and grow together with the community.
Were you did you find places where it was very difficult to fit the differences between different switching ASICs into that sort of common switch abstraction layer?
I would say that most of the control parts, right, like the common abstractions like layer 2, layer 3 functionalities, that was pretty easy for the community to agree to each other, right, even across very different generation of a hardware ASIC. Because normally those kind of abstractions are so well understood, right? There's not a lot of argument on what is a VLAN or what is a routing, right? It doesn't matter what ASIC you're talking about. I think we had more challenges on the newer functionality, right? Like telemetry, right? Which is a kind of something shiny and new, and there's a lot of innovation, right? And maybe that's not a problem. It's just a kind of nature of things, right? People are still innovating on multiple fronts. And they are not in really agreement because they're shiny and new, right? And so it took a little bit longer than we thought to kind of reach that community consensus, right? But I think again, once those consensus are reached, I think it's become a very useful thing across the board, right? I think that the impact is getting bigger, right? So I think that's what it is.
That's great. So that's a good lead into my next question. So there's been a lot of focus in the research community on bringing programmability to the network. And this comes in the form of smart NICs for end hosts and programmable switches such as Intel Stefano. So I'd love to hear from both of you your thoughts on network programmability and what role you think it has to play in cloud infrastructure. Do you see these technologies mainly being used by the large cloud providers in providing their infrastructure services? Or do you see these new capabilities actually being exposed to cloud customers so that customers can actually sort of build network programmability into their applications?
Sure. No, I think that's a great question, Alec. To some extent, network programmability is already starting to show up at the application level. If you look at where container networking has gone and some of the innovations in CNI, and you look at how we've integrated with Kubernetes, you can already start to expose APIs where you can dynamically update your network topologies and update what your containers network policy looks like in an API-driven fashion. And in the back end, that all runs into the smart NICs, right? And then goes and sort of changes policy on the fly in hardware. I think that trend is only going to continue. I think we're going to see a lot more innovation in the transport space as we go past 100 gig, RDMA and other hardware accelerated transports become a lot more necessary to get any reasonable CPU utilization out of these sort of high speed bandwidth elements. And as we start to expose more and more of that to cloud customers, you're going to see some programmability there in terms of what they can do with the transport layer. So certainly in infrastructure, this trend isn't going away. The networks are getting faster, and we're still going to have programmable hardware elements along with them. But I definitely think we'll see more from a customer perspective too.
And Lihua.
Yeah, totally. I definitely see the network programmability play a huge role in cloud providers. I think the ecosystem is going to broaden to not only the end host, but also the nodes in the network, right? Or maybe kind of just new places that we never imagined, right? So in the network devices, right? Because the ASIC are getting smaller and smaller, and it consumes less and less power. So stuff that couldn't show up before, now it's possible. Right, and I think part of the Sonic's goal, right, is also that enable that layer, right, because you need a common operating system to have that kind of abstraction, right. So I think that within our network, right, we're already starting seeing like new functionality coming up in places that you wouldn't normally think about it. Right, let's say top of rack doing a netting of VXLAN gateway, right, or like doing some load balancing capabilities, right. I think those things are showing up. As for the customers, right, I would say that they are getting probably just a different layer, right? So eventually that they want programmability, but maybe the layer of abstraction is going to be a little bit different, right? So maybe at a ASIC level, you have a layer of abstraction. At an individual node level, you had a little bit different level of abstraction, and maybe eventually to the customer, that abstraction is going to be different. Maybe the customer ultimately cared about a VNet or security group, that kind of abstraction, right? So I think it's the programmability, maybe it's not the end-to-end, but it's more layered infrastructure that customers are benefiting from it. But they are not really trying to program, say that, hey, I want this forwarding to that MAC on the next hop group onto this particular ASIC on this part, right? So I think that that's probably not the abstraction they would go that low, right? So those there are probably going to be variations there.
Okay, so now I'd like to ask you both to think a little bit about sort of taking a slightly more research focus and say, imagine for a moment that you're in charge of funding at NSF. What are the upcoming areas that you're most excited about that you would like to see funded? And what are the problems that you want to see solved that would change how we build, for instance, Azure's network infrastructure? So let's start with Leewa on this question.
So first of all, I think the NSF director, founding director, is a superbly powerful position, right? So, okay. So my wish list, right, top of it, right? I will definitely see debugger tools, right? So because if we are saying seriously that we're going to have the proliferation of programmability in the network, and you're going to write thousands and thousands of lines of code and to program thousands and millions of devices, right? Then the developers would need a good debugger tool to support that, right? And that's kind of a norm in the software development world, in the operating system, in the normal software side, right? You have WinDBG, you have GDB, you have a gazillion of other tools, right? And your compiler can produce symbol files, and you can set breakpoint, all those kind of things, right? So all those kind of abstraction is there. But in the networking space, right, we are still very much counting on some somewhat primitive tools, packet capture, latency diagnostics, scanning packets, right? Monitoring counters, right? So those things are useful, but probably not enough to kind of really do a deep debugging, right? Of hey, there's just a new piece of code that some guy inserted into one device and it caused a problem, right? And especially the network is all connected, and right. So I think that's a challenge, right? And I think that there's probably a lot of good fundamental research to be done in the compiler, in coming up with new abstractions in whatever language that is, right? To set those kind of thinking, right? So that would be my number one wish list.
Yeah, that's great. I mean, I can definitely relate to that, especially as network link speeds grow. Trying to debug these kinds of behaviors can be super challenging. So Daniel, let's hear from you.
First of all, I totally agree with everything, Leewa, you said. Debugging is only getting harder.
We're probably in too many joint debugging sessions together.
We probably are. But I think further, there's a lot of interesting stuff starting to happen at the physical layer here. We've become addicted to almost to this, inevitable speed growth of doubling the network bandwidth every couple of years, and yet that still remains relatively cheap for us. But we're running up on the limits of copper cables. We're running up on the limits of low power optics. I think, if I were NSF and looking, a little further forward, I think thinking about sort of what terabit, multi-terabit class links are going to look like to keep up with this space, while still having sort of silicon programmable elements associated with those, I think is going to be a fascinating area of research. I don't think, the physical network, essentially layer one and physical elements of the host can look like what they do today at those speeds. So
in other words, Moore's law is sort of starting to catch up in the networking space as well then.
Sure, until the next paradigm shift, right? And the question is, what is that, right? What does that look like?
Okay, thank you guys very much for your time today. It was really great to hear from both of you. And I think we're pretty much out of time. So thank you very much.
Thank you, Alec.
Thank you. Thank you, Alec.